What's up, guys? It's me, Sir Ernest, and today we will introduce the concept of linear oscillators. Okay, so first let's consider a particle in stable equilibrium at the origin, and we're going to describe that in a potential energy diagram. So the vertical axis is your potential energy, and then the horizontal axis is your position axis. And let's say this particle has a potential energy function, something like this. So as you will notice from the graph that the particle has a stable equilibrium, or the particle is in stable equilibrium at the origin. So that means if the particle is at the origin, okay, the particle experiences zero net force. And if, for example, if we place that particle in, let's say, towards the positive x-axis near the origin, let's say somewhere here, okay, so at this point the particle will experience a force that is to the left. So that means the particle in this position x will experience a net force to the left, so this force will return the particle to its equilibrium position. The same thing if we place our particle in this position x, the particle will experience a force exerted to the right. Therefore, the particle will accelerate towards the equilibrium position at the origin. So in other words, these forces always act opposite the direction of the displacement, and we call this restoring forces, because of the fact that these forces restore the particle to its original or to its equilibrium position. Okay, since any force function that has a continuous derivatives of all orders can be expressed as a Taylor series expansion as such. Okay, so the first the first four terms of the Taylor series expansion of this force is F naught plus x times the derivative of F with respect to x evaluated at the origin plus 1 over 2 factorial times x squared times the second derivative of the force function with respect to x evaluated at the origin plus 1 over 3 factorial x cubed times the third derivative of f with respect to x, again evaluated at the origin. And you can extend this Taylor series expansion. Okay, so in this case our f naught is the value of your function of your force at x equal to 0. Okay, also the derivative, the nth derivative, again, so this is the first, second, and third derivative of f evaluated at the origin. Okay, so because we know that this particle is in equilibrium at the origin, therefore the force exerted when the particle is at the origin vanishes to 0. Okay, so therefore if we're going to consider small displacements, okay, so that means the displacement from the equilibrium position is small enough, this can enable us to neglect higher order terms. So what does it mean? The x squared, x cubed, and higher order terms can be neglected. So in other words, these terms can also be neglected. So under these considerations, the force function can now be approximated to be equal to x times f, derivative of f with respect to x evaluated at the origin. So we show here that this force, this restoring force, is linear in nature, and uh, this enables us, or this approximates the commonly known as Hooke's law. Okay, because this function, or this derivative with respect to x at time at x equal to 0 is just a constant. So therefore, we can rewrite this as f, so function of x, equals negative kx, where here we define k to be the negative of this factor. So we input the negative sign here to express that this force is always the opposite direction of the displacement. So in our case here, if the particle is here, the displacement is along this direction. So the direction of the displacement is to the right. Therefore, the force is to the left. In this case, the direction of the displacement is to the left. Therefore, the direction of the force, or the direction of the restoring force, is to the right. Okay? As long as k is always positive. Okay? So in the next video, we're going to connect this to a spring mass system wherein this is one of the most simple, or the simplest, one of the simplest system that describes that uses this linear equation. Okay, wherein this consists of a spring. In this case, the k here will be the spring constant k, and this spring is connected to your particle, where the particle, or the mass, is what we call our oscillator. Okay, so that's all for now. I'll see you guys in the next video. Thank you for watching. Bye bye.